Good afternoon, everyone. So my name is Aydogan. So welcome to this parallel sessions, which you are right now in engineering session, if you're not aware of that. So we have two speakers, and I'll be the first one, and tell you more about what we've been doing at UCLA on photonics technologies, and with a specific emphasis on telemedicine and global health challenges. So I'll tell you more about what we've been doing. So let me first have some more contrast, because I'll be talking about imaging techniques that are going to be used for telemedicine purposes. So I'll be showing you some images and movies, so I need the contrast. At the center of our lab's work is lying actually the architecture that we have with the cell phone. So cell phones today are literally everywhere. We have more than 5 billion cell phone subscribers, as you can see in this world map. And what is quite interesting is more than 70% of these cell phones are being used in developing parts of the world. Literally, in my room in California, we don't have good reception, but in Africa, you will have probably much better, much faster as well reception. So this existing connectivity that we have today, together with the state-of-the-art of cell phones in terms of their hardware and software capabilities, indeed holds numerous opportunities, especially for healthcare, especially for global health challenges that we have. Imagine, for instance, that you had a microscope or a microanalysis tool that could attach to cell phones to look, for instance, at blood smears. You could diagnose malaria with such a technology, and this could help us, especially in developing parts of the world, which I highlighted as yellow, where most of these infectious diseases are still endemic. The same is true also for looking at parasites, looking at bacteria. These are small-scale things on the order of 1/1,000,000th of a meter. So you need microscopes that could potentially look at these things. And if you had these microscopes working installed on or attached to cell phones, you could really have a huge penetration of these advanced technologies. Just to give you the scale of the problem, co-infections, HIV, TB, and tuberculosis and malaria, they cause more than 4 million deaths a year. And if you add to this number poor drinking-related issues, we're literally losing more than 6 million deaths. And there are numerous opportunities where cell phones could penetrate and help essentially combat some of these infectious diseases or other conditions that we have for global health. And that's exactly the theme of our lab at UCLA. We're trying to provide new platforms for conducting telemedicine. And what you see on this slide is some of our gadgets, some of our microscopes that are installed literally on the cell phone to convert the cell phone itself into a microscopic imaging device. And I'll tell you more about this platform, what we've done with it, and what we plan to do with the same platform. But for the rest of my talk, I'll be referring to this platform as Lucas. Essentially, it's a platform technology which could be used for various different things. Before I tell you how it works and what are some of the results that we've got with this technology, let me go over some of the key features of this platform that make it quite different and unique compared to conventional microscopes. The first important feature of this platform technology is that it's lens-free, which means it doesn't require these advanced bulky optical components like objective lenses that you normally find in a conventional microscope design. As a result of that, these are fairly inexpensive, compact, and lightweight at the same time. This attachment to the cell phone, which converts the cell phone into a microscope, is on the order of 40 grams. And if your cell phone doesn't have a camera unit, you can have standalone microscopes as shown here. These are lens-free microscopes, which are powered through USB and controlled through USB, and they can provide distant resolution over very large imaging areas. So they are high-throughput microscopes, and that's quite important because most disease signatures are rare. I'll tell you more about this when I talk about cervical cancer or malaria imaging. They are really infecting maybe 1% of the cells or less. That's why you need high-throughput microscopes, and that's why these platforms, as I'll show you with some results, are quite important. And while we are creating these portable microscopes, we are also gaining some sensitivity because there is some nice physics behind these microscopes, as I'll briefly tell you, that also make them quite sensitive to especially small-scale things like bacteria, which is quite difficult to see. And finally, these microscopes are tolerant to misalignment. If you were to operate one of these things in the field and drop them on the floor on a sunny day, they would easily work if you pick them up. So that's kind of very important because you can't find PhD students or engineers to realign these things if you want to deploy them in real field conditions. So lens-free computational imaging, which is at the backbone of the Lucas platform, holds significant promise for telemedicine, but at the same time, it has some applications for ultra-high throughput microscopy needs, especially for something like Mehmet Toner's lab has been working, such as detection of circulating tumor cells. So there are non-conventional microscopy modalities that could also help us create extremely large 20 centimeters square type of imaging areas on a chip, as shown here, with these non-conventional microscopes. However, in this presentation, I'll focus on telemedicine and will not really tell you more about these extreme throughput microscopy modalities using lens-free computational imaging. Well, after this introduction, let me go back. And probably a lot of you are questioning, how can you see without the use of any lenses, without the use of all these optics that you normally find in a microscope, these small-scale things like 1/1,000,000th of a meter, these cells or bacteria? Well, because we don't have the lens or a magnification system, we essentially work with the shadows of these specimens. We detect shadows of cells or bacteria. What is quite different between our own shadow, which is pitch dark on a sunny day, as you can see, it doesn't contain anything useful. However, if you look at the shadows of specimen like cells, because they're tiny, on the order of a couple of microns, they are semi-transparent. They cast a unique shadow, which you can treat like a fingerprint. So if you look at particles or cells at the micron scale, at a scale that's 1/1,000,000th of a meter, they'll be casting these structured fingerprint-like shadows, which is the starting base for something more advanced for our microscope. So we detect these shadows to understand what's going on in a specimen, in a specimen like blood. If you look at blood, you'd be mostly seeing the shadows of red blood cells because blood is dominated by red blood cells. That's why these things that you see here are the fingerprint shadows of red blood cells. If you zoom in closely, you would be seeing every now and then a different shadow type, and they're going to be coming from white blood cells and platelets and other things. So based on this simple principle of imaging shadows, we can understand what's going on within a specimen and count cells, which might be quite useful to start with. But there's a limitation to this technique, which is as the cell density gets higher, these cells and their shadows start to overlap. That's where things get a little bit complicated. If you look at, for instance, the same blood sample, which is now a little bit more dense, on the order of 0.1 million cells per millimeter cube, think of a millimeter by a millimeter by a millimeter, there's around 0.1 million cells there. That's why the shadows start to overlap with each other. We can't really understand what's going on based on simply a shadow analysis, even though they are unique. That's the time to realize that there's nice physics behind these shadows, and they're not dummy shadows. They're actually holographic shadows of these cells. So they are holograms. That's the starting point of a very nice set of things, physical techniques, that can make more from these dummy-looking shadows. We can reconstruct them, these holograms, using computer algorithms that take a few milliseconds, for instance, to create something like this, which you're seeing microscopic images of these cells reconstructed from their shadows, which exactly matches to a conventional microscope image, except there's no lens, there's no bulky optical component to it. So to wrap up, there's some nice physics behind this platform, which essentially is relying on partially coherent holography, which means we're not even using lasers for this thing. We're using what we call LEDs, light-emitting diodes. The things that you have at the back of your cell phones, whenever you have a new email, that thing that's blinking, it's an LED. So we're using those partially coherent sources to create these holographic shadows, which are quite unique to start the reconstruction process. It's installed on a cell phone using the cell phone CMOS imager here. This is a 5 megapixel imager. Most of your iPhones are better than this. If you don't want to modify your cell phone, you can have a standalone unit like this, which is on the order of 45 grams, to work as a microscope. Or we can go to extreme field of view using benchtop systems, using this nice set of principles. Well, we've done a lot of things with this platform. Now I'll start to show you some of these applications that we have taken this platform for. Of course, we looked at blood cells. These are 3 different kinds of white blood cells. which you see their shadows. Then you quickly reconstruct their images as shown here in both amplitude and phase, which is an important property of holography. It gives us two different channels. It has the phase contrast ability, especially useful for looking at small things. And then they nicely match to a conventional microscope. I'll start showing you some lower resolution images on the order of 1.5 micron resolution. But then later, we'll tell you some stories about how to make the resolution even better to go to sub-micron scale things and achieve a resolution close to 0.5 microns. So because everything is digital, this platform also works as a cytometer, as something that can count cells. And what we've done with a microscope like this is to look at blood and count blood density, red blood cells and white blood cell densities, which nicely match within a few percent error to a hematology analyzer. And these are quite important tests because many diseases show their signatures in increase or decrease of these cells. And you can do more interesting stuff and understand the volume of each cell at the single cell level with femtoliter accuracy. And you can do hemoglobin measurements and many other things that a hematology analyzer could do using these platforms. One application that we have taken this for, specifically for global health, is for monitoring of HIV-positive patients. This is something that also relates to an early speaker. Mehmet Toner's lab has done fantastic work on the biochemical assays, especially for monitoring HIV patients. An important problem for monitoring HIV patients in resource-poor countries is counting their CD4 lymphocyte density. A CD4 is a white blood cell type, which HIV unfortunately kills. That's why normally we have around 1,000 CD4 cells per microliter. But once HIV kicks in, this number drops to a few hundred. That's when a flu can really be quite detrimental. That's why, according to the World Health Organization, every 3 months you have to have that CD4 counted. That's, of course, a costly process. We have gold standard technologies for this, such as a flow cytometer. It's a bulky technology. It works very nicely. However, it's challenging to miniaturize it. And the running cost per test is not that low. It's on the order of $5 to $10. What we've done is we've taken biochemical assays, biochemistry assays, very similar to what Mehmet Toner's lab has been pioneering, and specifically have designed these microchannels which capture CD4 cells through antibodies. So once you inject whole blood and wash it out, you will only capture these CD4 cells and other lymphocyte types that you're interested, and then count them using the Lucas platform using Lensfree imaging. Actually, our collaborator from UC Davis is a postdoc of the Toner lab. With this platform, we can look for various different things. This is actually a chip, the surface of the chip. And you see these red spots here. Each one of these red spots is a certain antibody, in this case anti-CD4 or anti-CD8. We were looking after CD4 and CD8 lymphocytes. And they're captured from an HIV-positive patient. If you zoom in, you would be seeing these holograms, which are reconstructed and counted so that we could understand what's going on. And this is a close-in image of the same thing. In this study, we were looking for specifically the ratio of CD4 to CD8 lymphocytes and its indication to the state of the disease. For healthy patients, this number was very high. But for HIV positives, the CD4s were depleted. That's why the number dropped. Actually, it dropped in severe cases to less than 0.5, which was when you should start a therapy. So this is a good example where by combining lens-free computational imaging, which creates these tiny microscopes that are field portable, with spatial microfluidic devices, you can create something that is quite cost-effective for handling something very challenging, like looking for subpopulation of white blood cells. Another important thing that this platform could be quite useful is, of course, for looking at bacteria. And for this, we have a unique advantage. That is, we can look at a large volume with phase sensitivity. If you look at an E. coli, that's only around 200 nanometers in diameter. It's tiny. And if you surround it with water, it's like trying to see a phase object, which you can't really see, unless your microscope is equipped with that. To give you a comparison, using a conventional microscope, a high numerical aperture one, you can look at some water that is contaminated with E. coli. To guide your eye, we put these red circles, which show you an E. coli within your field of view. The same field of view can be imaged with Lucas with much better contrast, because Lucas is a holographic technique. It works like a phase contrast, and it's a huge advantage, especially for looking at these small-scale things like bacteria, in drinking water. And these are some reconstructions based on these lens-free shadows, and which nicely showed the E. coli signatures with much better contrast than a conventional microscope. This is a conventional microscope comparison, and we put these red arrows to guide your eye. The same is true for different parasites. In the United States, the most common hospitalization actually occurs for Giardia and Crypto. Those are the two parasites that infect the most number of patients in the United States. And these are some of their holograms and their reconstructions for the same goal of achieving actually large field of view, high contrast imaging of these bacteria. Toward the end of my talk, I'll come to some other technologies which bring in some more specificity to this problem, where we can go after a certain parasite type and then leave the rest of the junk behind. So far I've talked about a platform like this, which in a very compact, lightweight, and cost-effective manner can bring us a distant field of view and a distant resolution together on the order of, again, 1.5 micron resolution with a very large field of view on the order of 24 millimeters square. 24 millimeters square is a large field of view. It's on the order of 20 times larger than a conventional microscope with a similar resolution. And it's common that if you want to go to higher resolution, there's one immediate trade-off in microscopy, which is your field of view gets reduced. So if you want to have higher resolution, you have to live with smaller field of view. I'll tell you now what we've done to keep the field of view the same, quite large as we want, but go to higher resolution by a factor of 2, 3, so that we can reach even better resolution at the sub-micron level. Of course, to do that, we have made our device a little bit more complex, going from a design like this to something like that. However, it's still cost-effective and lightweight in the sense that this entire design, which goes to around 20, 30 millimeters square field of view with sub-micron resolution, is less than 100 grams. It's still USB powered, and it has many light sources in it. Despite, in the first part, I've shown you results with a single source, with a single light-emitting diode. Now we have installed there some 20, but it's still cost-effective because each one of these LEDs, light-emitting diodes, cost us on the order of $0.2 and even less in higher quantities. That's why it's still very compact and cost-effective. And there's nice physics behind this, which essentially is using some of the technologies you find in security cameras at an airport. If you're walking in an airport and there's a security camera at the corner, if you're standing still because you're far away, your face won't be resolved. It will be pixelated. But if you stare at the security camera and slightly move left and right while staring at it, we can capture a movie of your face, even though each frame is pixelated, combine all of these frames and create a much higher resolution of image of your face so that we can recognize you. This is called pixel super resolution in literature. So we've applied similar tricks to create higher resolution holograms by essentially turning on these light sources one by one. It's equivalent me walking left and right while staring at the camera. The specimen is static here, but the light source is moving. That's the same effect as me moving across the hall from a camera. That enabled us, without a trade-off, to go to a much higher resolution at the sub-micron level, but without trading off the field of view. So this is the same field of view that you see. It's got a scale bar here, a millimeter. So you're looking at the blood smear. It's the same thing that malaria is diagnosed today. There's a monolayer of cells, mostly red blood cells. And the technician is required to look at the morphology of each one of these cells to see if there's a parasite signature within the red blood cell. But the problem is only 1% of the malaria, of the red blood cells are infected with malaria. So you have to look at least 1,000 of these field of views. If you digitally zoom into this large field of view, we can reconstruct from one diagonal to the other with sub-micron resolution, seeing these clusters and these subcellular features of these cells. And that's, again, a unique paradigm in the sense that the field of view and resolution are decoupled. We can achieve the same resolution over a larger field of view or better resolution over the same field of view with next-generation sensors. And again, this is quite important for malaria diagnosis because of the fact that malaria is quite rare. This is a comparison between a conventional microscope and our Lucas microscope in terms of diagnosing or in terms of spotting these parasites in in red blood cells over, again, a very large field of view. This problem is quite interesting because in sub-Saharan Africa, believe it or not, 60% of the malaria cases that are reported are false positives. So if you want to claim to invent the next generation technology, you can flip a coin, and then the decision will be almost as accurate and quite cost effective. So of course, we can do much better with a microscope like this, which is quite high throughput and can give you a large field of view digitally so that you can try to automate the decision making by spotting these parasites across a very large area. The same is true for actually looking at cervical cancer and pap smears. This is a pap smear which is used for cervical cancer diagnosis, and it's actually a field of view that's on the order of 30 millimeters square. It's increased from my previous results because this microscopy modality is following the Moore's law, in the sense that every time I get a better sensor, better imager, it's going to improve my quality of image without any trade-off. And that's kind of quite unique in the sense that it really digitally follows the Moore's law. Here we gained 6 millimeters square field of view without losing anything. Because of the flexibility, we can do more than just plain imaging. We can do tomography with the same principles. So it's the same idea behind X-ray computed tomography, where your body goes in and there's a light source, in this case an X-ray in X-ray computed tomography, which rotates around with the detector rotating and capturing different planar cross sections of your body and to synthesize a three-dimensional image. The same ideas that I've been showing you are applicable to tomographic imaging as well. So that by having a light source rotate, and at each position with slightly jittered light source to capture a super resolved image of that cross section and move to the next one, we can synthesize actually a tomogram of a large volume. This is actually a tomographic movie which shows you 5 micron particles imaged, and what you're seeing here at different parts are slices of the same volume being imaged with sub-micron lateral resolution and sub-3 micron axial resolution. But the most important thing here is the volume. We can screen very large volumes on the order of 15 to 20 millimeter cube, which is quite larger than a conventional microscope, at least 2 orders of magnitude. And these are some other model organisms that are being imaged. This is a C. elegans movie. It's a model organism which is quite frequently used for especially drug discovery purposes. And you can see a tomographic movie of that animal while you're slicing through its body. And this is entirely done, again, using lens-free computational techniques. Because of its simplicity, you can also install it on a handheld field portable microscope. This is actually a unique microscope that it can enable large field of view imaging in X, Y, and Z using an architecture that is quite cost effective and on the order of 140 grams. So it works quite similar. We have lots of light sources here which are digitally turned on. Each one of these is a light source. The sample is inserted from the side. And if you focus on this movie, all of the light sources are attached to a bridge, and they are being electromagnetically actuated so that we capture a super resolved hologram of one angle and advance to the other one. As a result of that, we can have a field portable microscope that can look at cells in 3 dimensions and slice them up in Z, which again is quite nice, especially considering the fact that it's a quite inexpensive and field portable device. So what I've shown you so far were microscopes that are working based on digital holography and shadow imaging to look at a very large field of view using lens-free computational techniques. And again, the important thing about these platforms are their impact, especially for global health problems, their potential for combating some of these infectious disease problems. But what I've left aside was another important microscopy modality which is frequently used in especially biomedicine, which is fluorescent microscopy. So fluorescent microscopy is a spatial modality which has these fluorescent dyes that specifically attach to cells or bacteria or tissue samples to make them glow with a specificity that you are comfortably saying it is a certain cell type. That's why it's quite important, especially for detection of bacteria in, for instance, milk or water, to use such existing technologies. What you see here is a fluorescent microscope that is attached to the back of a cell phone. It's quite different in physics than what I've been introducing to you so far, in the sense that this is actually around 30 grams, attaches back to the existing camera unit, and the specimen is inserted from the side. And there are some light sources here, which are also LEDs, which are used to excite these fluorophores, these chemical components which emit light once excited. The sample is inserted from the side, but it also acts like a waveguide, so that the excitation is uniformly distributed through the sample, which makes us quite successful, actually, to get rid of this excitation light using a very inexpensive filter. That's a $1 filter that's inserted from the side, which gives us the large rejection of the pump and a nice dark field. So what you're seeing on this slide are some images captured with this platform. This is actually a whole blood sample. These are white blood cells that are labeled. If you zoom in, you would be seeing some of our images with a very nice dark field. And these are some Giardia samples, waterborne parasites, and their microscope comparisons. With the same platform, you can also do cytometric measurements. So rather than looking at a static field, you can actually flush through microchannels your specimen and capture a movie like this, which is captured with this with the cell phone attachment here. And we're doing actually counting in whole blood these labeled white blood cells as they're flowing to understand their density in whole blood, which in this case nicely agrees after a few minutes of flush to a hematology analyzer looking at the same blood sample. And with the same platform, you can actually integrate more advanced technologies like that are going to be specific for a certain pathogen type. What we've done here is we've used these microcapillaries. These are tubes which suck liquid, or you can pump through these channels some liquid like milk, which might contain some, let's say, E. coli particles that you want to detect. The inner surface of these channels are functionalized with some antibodies which are specific to a certain E. coli type in this case. As they're flushing through, E. coli particles are attaching to the surface, and we label quantum dots, which gives us fluorescent signal intensity, which correlates with the contamination level in that liquid. That's exactly what we've done here, and we've actually measured down to, roughly speaking, 5 to 10 particles, E. coli particles per milliliter, which is quite sensitive in the sense that if your water sample had contamination larger than 5 E. coli particles per milliliter, this would be sensing it through a system installed on the cell phone. To wrap up, I've introduced to you a platform technology, which we call Lucas, that can bring in more advanced microscopy tools and microanalysis tools at the back of a cell phone. And in a very compact, cost-effective, and lightweight manner so that you can deploy these things in remote locations in resource-poor countries, especially important for various different infectious diseases like HIV and malaria. But the future is, I think, more exciting than what these individual microscopes can provide us, because the price point and the simplicity of these devices would probably make microscopy 2-3 orders of magnitude wider scale deployed in different parts of the world. So you can think of this individual microscope that I'm showing here as a PC in the sense that it's compact, it's cost-effective, and it will be soon used by many more people than it was initially designed for. So this will help us to increase the number of personal microscopy users by several orders of magnitude from where it is right now. And this will create us opportunities to connect them together digitally to form what I call the micro-internet, in the sense that what we can do with these platforms deployed in large scales, with all the information exchange that's occurring between our servers and these microscopes, would put us in a unique position, like Google is positioned today, to look at the microworld in unique ways that we haven't yet considered. So this is kind of quite exciting for my next 5 years of research. With this, I'd like to acknowledge all of our graduate students and postdocs behind this work, as well as our funding agencies, and thank you very much. Questions? That's a great question, and your insight is exactly right. What is different from radar type of approaches, like synthetic aperture type of approaches that I'm sure you're pointing to, is this. At a given time, there's only one LED on. So let's forget about the rest of the LEDs for a given time, so that there's one LED on. It is creating, for each one of these cells, a plane wave, because they're far away from it, and each cell, with being having a diameter of 8 microns, we'll see it as a plane wave. And this plane wave is equivalent to the quality of a laser for the cell, but not for the next cell. Yes, so each cell, even though you are using sunlight, then it is essentially scattering this thing, and then there's some background light which is coherent. So this scattered light and the background light creates a hologram, which is technically in optics community, it's called an inline hologram. Inline meaning that you don't need two separate laser beams. It is inline scattered light interface with the background. So that's so far one LED. It gives you a nice hologram, which is exactly the shadow. What happens as I turn on different LEDs is this. Exactly like the ceiling, if you shift the ceiling light from left to right, my shadow will shift. That gives me the opportunity to use pixel super resolution tricks to digitally synthesize a smaller pixel size. Another way of saying this is, I take a 5 megapixel imager. At the end of the process, I create 300 megapixels. So with this technique, we are now generating 3 gigapixel images. And that's not interpolation, that's useful pixels. So there's not a 3 gigapixel imager yet, but these are giving us the opportunity to look at an image that is, let's say, 20 centimeters square with 3 billion pixels on it. That has an effective resolution of 2 micron. That's phenomenal space bandwidth product. Thanks. That's a great question. So it depends on the modality. Your computational needs are different. The next generation of our fluorescent microscopes are now running on Android phones. So Android phones are having graphics processing units. Why? I'm not sure, because most teenagers want to play games with them. So the Android phones that are coming out have already these advanced processors which are qualified to do image processing. So most of our new gadgets are, this is not an Android phone, but the next generations are, and they're going to be running some of these processing on the cell phone. The rest, especially something like this or that, super resolution microscopes, they're demanding on computation. So the idea is to compress holograms and go to a GPU server. So we use graphics processing servers for going back to a reconstruction of, for instance, one of these field of views within around a second. So GPUs help us to improve the speed by close to 50x, 50 times.
So how long will it take to generate an image?
For one of these super resolution, sub-second. Computation.
May I also ask a follow-up question? Would you also consider developing standalone applications, units, instead of attaching these imaging apparatus into cell phones? Are you considering to develop standalone units?
That's a standalone unit that doesn't attach to a cell phone. It has USB powered. So if you are having a small laptop or even a smartphone with a USB entrance, you can just have a cable that controls it. So this is actually a standalone unit, similar with this one.
How carefully do you have to align the fibers to the LED?
That's a great question. All of this work is actually put together by my undergraduates. That answers in a different way. But essentially, computation helps because we don't need to worry about the alignment. These fibers are put together. We don't assume that their spacing is known. Because once you capture a holographic pattern, like a shadow, next time you shift it, it shifts. And I can understand the shift with sub 100 nanometer accuracy without having the resolution, because this is a correlation problem, which is not diffraction limited. So my accuracy in understanding the shifts does not assume anything about the fibers. It just looks at 2 frames where things have shifted with respect to each other. And that is very accurate estimation.
Do you have a thickness limit on the sample
That's a great question. Actually, all of these microscopes that I've shown, except this one, which I didn't talk, are transmission microscopes, which means if a sample that is thick wouldn't work. So if you're trying to image skin, you couldn't because they're not transparent. So these are transmission microscopes, good for imaging cells within microfluidic devices or within a liquid, but bad for imaging tissue because tissue doesn't let light penetrate easily. That's why we have not talked here, but we have created some other microscopes which are computational, lens-free, and they work with reflection. Their geometry is a little bit different, but this is actually one of those. That's why you have an upright CMOS here that does reflection imaging. Not quite, in the sense that, well, it has some some relationship in terms of spatial coherence and temporal coherence to a slit experiment, and the governing rules in terms of if those two slits will interfere with each other or not are exactly the same here, but it's the physics is the same in terms of partial coherence of light, but the geometry is quite different than that. Most people also confuse this with pinhole cameras. I mean, I'm a little bit getting technical here, but some people think this is a pinhole camera. In the old times, one way of actually painting nice pictures was to have a pinhole, look at the scene, and then based on light, you could draw. And this is kind of like a nice trick. It's quite different. I use pinholes in this geometry, but not for imaging purposes. In a pinhole camera, between the scene and my detector, there's a pinhole acting like a lens. Here, the pinhole is above this object. So my pinhole is here, and that's my object, and that's my imager. So it's also not quite different than pinhole cameras. But pinhole helps me to qualify for playing with the spatial coherence requirements in a very simple way. Pleasure.
Okay. Pleasure to be here and an honor to be here. I guess representing the Midwest, just to prove that there is research going on in the Midwest universities also. And I'll be talking about autonomous cars and the future of driving, an area that I've been involved in for over 15 years. And with the help of a lot of good graduate students, we have covered a lot of different types of cars and other wheeled driving entities throughout the years. Let's see, oops, other way around. Okay. So just to bring you to autonomous cars, since we're all tuned to medical type of issues and biological type of issues, just to go in some totally different direction. So the question may be asked, why autonomous cars and more cars? It all started with people saying, okay, let's try to push more cars through the highways and not have to build new roads. So the first sort of thoughts about autonomy in driving was in the context of highway systems, and the first terminology used was automated highway systems. But it goes to more than that, and obviously the technologies that are used have sort of a trickled down to even the type of cars that we are driving today. So one of the concerns now and issues now that we think that autonomous cars can address is safety. You won't have distracted, tired drivers, and you won't have the drivers taking too many risks. Hopefully you can design your systems, your cars, to be much more reliable. And you'll have what we do demand, which is reliable arrival and departure times, just because the roads are going to be hopefully filled with these autonomous, bright, brilliant cars. There is some goal of saving energy, having cleaner air, and this can also be sort of pushed due to autonomous cars. And all sorts of applications that may be of interest would be they can find parking, can drop you off, come when called, easily carpooled. So you can imagine being dropped off at the restaurant of your choice without having to think about I know where will I leave my car, and when you're done eating and drinking, you can call these, you can just have a call to the car, and the car will come and pick you up, sort of the image of the horse that you'll whistle for, and it'll just come galloping up to you. And a lot of issues about convenience comes to mind if you have autonomous cars. Now, we did see earlier, and I think the first presenter actually started off with a little clip from a science fiction movie. And I think there is a gene that forces you, certain speakers, to have that type of irrelevant clips, movie clips to have. And I'm a fan of science fiction movies myself. So among all the ones that I've collected, I tried to pick one that was appropriate. And let's see if I can get it started. Oops, no. Okay.
System initialized. Destination, please.
Okay, so that was from a science fiction movie that I picked that I thought was appropriate to the venue of this meeting. It's from a movie called Time Cop 2, and you can see the imagination of the people that put it together. You have this big, hefty-looking science fiction-ish car, whereas we know now that we can get that type of behavior from cars that look very much like the one you're driving now. And going back in history, usually in articles about these things, one always sees this 1939 New York World's Fair, and I believe that picture at the top of the screen is from there. And GM had a stand and had a demonstration of using technology of that time. And I can't really imagine what was available, of showing that in the future, said GM in 1939, we will have cars where you can see that, I believe they're playing Scrabble there in the car. There have been a lot of developments since then in the 60s and 70s from the very university that I work at. Professor Robert Fenton did a lot of work, and we can quote from a number of researchers throughout the world, both in Germany and certainly in Japan. There was a lot of developments. In 1995, Carnegie Mellon University had what they called nav lab that traveled on the highways and showing that it can be done with a human, of course, as a backup, as a very tired backup, because it was trying to catch the errors and so on. And along the years, a lot of developments were reported, and I got into this, as I said, about a little bit more than 15 years ago, and we participated in a federal highway-sponsored research starting from 95 or 96 or so, and eventually ending in 1997 with a demonstration on I-15 in San Diego, where a lot of different groups around the country participating in showing that that cars could drive the road, at least in some segregated lane or a segregated pair of lanes, as you can see on I-15 there, where the two cars that were built for my group by Honda demonstrated that they could follow each other, form a convoy, and in fact pass each other totally under their control, under their decision-making in trying to get from one point to another on a 7.5-mile stretch of I-15. A lot of years have gone by since then, and the research and acceptance of autonomous vehicles on the road has ebbed and flowed, as you may say, through the years. We have been involved in developing a number of these cars with the graduate and undergraduate students in my group. And there you can see going from a huge army truck on the top left corner to various size wheeled robots maybe. And at the bottom right corner is actually a series of robots that Aselsan built. And we participated in a challenge that was in Australia, a robotics challenge in Australia, together with Aselsan's group. In fact, as a group coordinated by Aselsan, which when I talk about this in other venues, have to say, well, that's a Turkish company. I guess I don't have to say that here. So, a series of cars with lots of different types of sensors, radar, LiDAR, and eventually, closer to these days, the use of GPS and wireless connection in finding its location on the road and following a map were all the issues that we worked on. We perform experiments at the Transportation Research Center, it's East Liberty, Ohio, large track on which it's feasible to do these types of things. We, of course, perform experiments at the large parking lot at Ohio State University. At the left, you see two cars, both autonomous, one more autonomous than the other. The one in the front is one that we used in a program called the DARPA Urban Challenge, which some of you may have heard about because it received a lot of attention. And the one behind that is a newer car, which is actually totally self-controlled as far as speed and brakes go, but the steering is done by a human, so it's sort of semi-autonomous. We also do experiments together with Ozcan University in Istanbul, Turkey. And there you can see the lab there at Ozcan, and one of the cars being displayed on the campus of the university, where we continue to collaborate with a group there and continue developing some of our ideas. Okay, so historically, all analysis has been for simple, clean situations. One can claim that you will solve problems like the one on the left, but truthfully, all we're managing to do is still sort of the problem on the right. This figures I always find interesting. They have just tell you where it's from. When DARPA got into the autonomous cars challenge business, which was like 2003, where they announced the first grand challenge, and then eventually in a couple of years down the line, the urban challenge. The type of picture they showed was the one on the left, saying, here is the type of problem we will solve. Well, that's still too ambitious. And science progresses in small steps. And yes, we can handle situations like you see on the right, where you have maybe 3 cars, and you want to sort of figure out who has precedence, who will turn, who will stop, what will happen next, type of things. Let me show you, just hopefully to illustrate that this is not that easy a problem. This is from the DARPA Urban Challenge selection rounds. What you have there is a test area where there are a bunch of human-driven vehicles going around a circle, and anybody else's autonomous vehicle is supposed to come through the middle, stop at that stop where my car has stopped, and then make a left turn, a right to our right as we're watching, cutting through 2 lanes of traffic. You can see the tail end of one car going left. There will be cars also going right in a closer lane, and also not hitting that wall that we're standing behind. So, and as the car goes by, what I find sort of cool is that you'll see that there's nobody in it. Hopefully videos work. Well, sometimes not. Oops. I asked for help. It doesn't click on. Can we just go back to the folder? I can just pull it out from there. Okay. Well, what you saw there was, again, part of the rounds in the selection process of the Urban Challenge. And you can see the type of problems one encounters, which is, again, lots of traffic with human-driven. You can't quite figure out exactly what they may be doing. And you may... you may deal with not just the pathway that you're selecting, but also evading, hitting other drivers. Since the Urban Challenge, which has been a few years ago, a lot of new developments around the world. One is, of course, the Google car that we keep on hearing. The Google car is based on totally vision technology. No wireless connections, no integrated driving with the traffic. It just creates a big image of what's going on around and tries to drive through it. And there are a number of these on our streets now, since Google has invested a lot of money into this. Another activity supported by the European Union is an Italian effort, and you can see the 4 electric vehicles that started from Parma in Italy and went through Russia and drove all the way through Shanghai. So it was from Parma to Shanghai autonomous. It was basically the first car leading the way, the other cars following and being autonomous. But it was a fantastic experiment, I feel, and we were certainly impressed. So let's talk about some of the issues that we have dealt with during those years since the Urban Challenge. We have been looking into situations for driver intent modeling, just trying to simply decide when a car approaching us is going to stop or to turn or to go through an intersection. This is the type of research that is indeed being supported by a lot of car companies, where you want to figure out the intent of the other driver so that in the last 50 milliseconds or so, you can provide a warning to your driver saying, uh-oh, that other car is going to run through a red light, or not stop at the stop sign. So you have a very short duration to figure out what the intent of the other driver is. And it is a fairly hard problem because people who want to break the law, let's say, by driving through a red light, don't necessarily drive smoothly. They sort of do things furtively. So it's fairly hard to estimate what they're going to do. But this is the sort of thing that you and I do daily when we drive, especially in Istanbul traffic. So the direction things are going is sort of a collaborative driving experience. And throughout the world, there have been experiments that are starting on that. This is called the GCDC, the Grand Cooperative Driving Challenge, which was in Holland. And in fact, a group from Turkey did participate. We supported them. One of the cars there, I believe the sort of second car on the right, is the one that actually was taken from Istanbul to Helmond and in Holland. And the exercise is something like this. They closed off one section of the highway, and the car driving at the very front sends by wireless a velocity profile. Sort of says, okay, good, drive this fast, and then starts increasing, decreasing, and that sort of thing. And all the cars following it will pick up that through wireless and use that as their speed command without human intervention. So this is sort of a first step in collaborative driving. We are interested in a little bit more than that, and we are interested in sort of human beings maybe entering this group and behaving differently, and how do we deal with that? A little bit more mixed traffic type of issues. And here are two of my cars that I mentioned before in an experiment that we did with 2 autonomous cars and 2 human-driven vehicles, where we're trying to form a convoy with 3 cars and a human driver intervenes. And I'll show if it works out, a video of that. Just to talk a little bit about the development procedure that will get to this point, we basically start off inside our labs where we have a facility on which we can run lots of wheeled robots. And it looks like a little town, let's say. And we can do experiments with different levels of autonomy, all provided to the robots. So the robots know the rules of the road. They have a map of where to go, and we tell them, okay, you go to point B, and then the rest they have to figure out using the software that each one has. And they also have to figure out what everybody else is doing. And they have to also figure out the traffic lights and the intersection precedents and things like that. All the sorts of things, again, as you and I do sort of naturally or semi-naturally, but we have to sort of codify this and create the rules and the software for the individual vehicles to use. So our development procedure starts with doing it first in simulation, then in lab robots, then taken out to maybe a big parking lot that you see on the left bottom section there, where I've shown a figure 8 that we will run our cars through. At the middle of that figure 8 is a traffic light, sort of a homemade traffic light. And at the very top, there's a stop sign. So the idea is 3 of our cars in a convoy will approach the stop sign. But because of the rules of the stop sign here in the US, a human-driven car can and will interfere and create a new situation for them to figure their way around. Let's see if this works. No. Help again. I get out and pull the video up. That's the one at the very right, yeah. Okay, you can see the three cars. They stop at the traffic light, and they have formed a convoy. The first car is human-driven. Second car is fully autonomous. Third car is semi-autonomous, as I explained. They're following each other, come to the stop sign. A human-driven car approaches, comes to the stop sign. First car goes, that's the leader. Second and third car, which are autonomous, come up to the stop sign, stop themselves. Human-driven driver goes. Two cars are now left leaderless. The leader is actually way ahead. Human-driven car is slower. You see the same thing now from a different angle. Three cars, the two cars you see now are both human-driven. The first is our human leader. The autonomous car comes and stops at the stop sign. It figures where the stop sign is because it has a map. Human-driven car goes. What you're watching is totally autonomous. And they're stuck behind the human slow driver, the reluctant convoy. And way ahead, you don't see it on the screen right now, is the leader of the two following cars, just trying to see. If there was a situation warranted, they could possibly pass the first car, but right now they are in a single road. They come to an intersection, at which point the human car turns left and ours rush to catch up with their original leader. And that was also automatic. I mean, they have to do that. Okay, just going to show. Okay, we're done. Back. And okay, so our vision of autonomous vehicles in dense, mixed traffic urban environments is the following. We will have an autonomous car, maybe a few of them, and there will be other cars that can sense their surroundings and tell you stuff. Not all of them will be autonomous, but some of them will cooperate with you in trying to provide you data to tell all that's going on in all the multiple lanes. From this, you put together an image of what's going on around you in that world and decide what you want to do. So you have to understand not just where the cars are and what they are doing or what may be doing, but also what the human drivers would want to do, would intend to do, legal or not so legal. And our vision is that, again, you'll have sort of regions where these things happen and all the cars will be connected. Depending on market penetration, we don't know how many of these autonomous cars will be there, but they will be there. And certainly the networking between the cars where they pass information to each other about their location, speed, direction, and possibly with their destination will be transferred to each other. This is already on the way, certainly in Europe and coming up in the US also. We'll have probably legislature that will say, okay, from now on, every car off the line will have to provide this, what is called here I am signal. Here I am being, okay, I'm here on the map, I'm going in this direction, and here's my timestamp type of information. From that, other cars will put together various things. So, what is the future? There are things that are easy to guess. Optimizing for energy savings, cleanliness, which means both in route selection and speed selection. These are coming. Autonomous convoying on highways, probably that's coming also. The picture you see there is an experiment that we were sort of linked to in Japan, where you have 3 trucks following each other very, very fast and very, very tight. So tight that there is energy savings in that. If you remember how cyclists go as a team sport, they go in the wake of the one in front of you. That means that they don't have to push that hard. Same thing with trucks. If you're driving 60 miles per hour and you're just going sort of 3 meters behind the truck in front of you, you do save a lot of fuel. And if you can do it with multiple trucks, you see, and all the trucks on all the highways do this, that's a substantial amount of fuel. Except you're not going to find the drivers to do this with a 3 meter spacing for hours at end. What's the answer? Well, they have to be autonomous. So call me, as they say. Not so. So that's. I'm sure is coming. Not so easy to guess this full integration of autonomous cars into human traffic. It's nice to do research on it. Don't know how much of that is going to happen and how soon. Also, estimating the human driving intent directly from the driver's behavior. That's also new. It may be coming. After all, you can do direct real-time analysis of body posture, gaze, or you can even collect data on EEGs in real time to see whether you may be intending to do something bad. So whether I'm going to try to go through a red light, maybe you can tell from the EEG. And if you can collect the data fast enough, your car can broadcast the information saying something like, oh, I think my driver is going to drive through this red light. So if you're scared of robots coming into your room and injecting you with things, which is what we heard this morning as an item, forget about that. I can tell whether you're going to go through a red light. So with that, I'd like to, since I started with a science fiction movie, I'll finish off with an appropriate science fiction movie about bad intent in driving and say that in the future we may get to this sort of thing. And I don't know, again, whether this is going to start or not, but we can always try. It did. Okay, so with that, I'll stop. Be glad.
You have done remarkable work in solving the technical problems. Can you guesstimate how long it will take to solve the societal acceptance and the legal problems that come up with this, especially in the United States?
Well, we heard mention of 2 lawyers here. The president claimed he was a lawyer. No, this is an issue of what the laws will provide. One thing I can say is that Nevada has just enacted legislation allowing, actually directing their traffic department to come up with rules under which autonomous vehicles will be able to drive on their highways. So that's sort of a first in the US. So Nevada actually has, and unfortunately I don't have a picture of it, I've seen a picture of it, a sign as you enter the states. As you enter the states over some highway, it says, autonomous vehicles welcome. So that's the first. Of course, somebody can say, well, who cares what highways in Nevada are not that dense traffic. But anyway, so that's a first. But I have driven, and the vehicles exist now around the world. A number of car companies have produced vehicles that have active lane, they call it an active lane departure warning. And you get in the car, and the early ones that were used on trucks just give you a buzzer when you're sort of drifting out of your lane. What is in the market available in cars right now in Japan, and I believe in Europe, are systems where if you don't listen to that buzz, as you're drifting off the lane. It actually steers you just a little bit back into the lane. Sort of pushes you, shifts you into the lane. It keeps on buzzing at you because of legal issues. But practically, that car is driving itself. I mean, you have your cruise control. You have the next version of adaptive cruise control, which some of you may, I mean, it's available in the US right now in higher-end cars, where when you encounter a slower car in front of you, you don't have to get out of cruise control. It will adjust its speed with the slower car. Okay, so speed is controlled. And I can push you back into your lane, nudge you back into the lane, as they want to call it. That's autonomous driving. Okay, so depending on the laws, but of course, the US has the deep pockets phenomena where people get scared. I mean, car companies get scared that they'll be sued if something bad will happen. So they're sort of reluctant to go. But those trucks you'll see in Germany, you'll see in Japan, and then eventually you'll see here also.
Did you consider using this type of cars for military applications?
Yes, the answer is yes.
What type of applications? Battlefield, maybe another type of application?
Well, I mean, the grand challenge, which I didn't talk about, was off-road driving, and it was pushed for off-road convoys and so on, and we did participate in that, and so convoying has always been a push from the military, and you probably won't have tight convoys for the military. You'll have sort of larger direction. But the vision there is that you'll have one human driver in the first truck, and then you'll have maybe 3 trucks following. And the risk is I mean, you're not risking human beings except maybe that first driver. And they won't be that tight because you don't want to get hit with. So convoying has always been a military. The other military thing is, just for guard duty. Guard duty has always been around there, not just for vehicles like this, but just wheeled robots going around or taking images. Yes, sir?
What do you think electromagnetic pollution after that technology?
Pollution? What sort of pollution?
Electromagnetic?
Oh, electromagnetic pollution. Well, the National Academy of Sciences had a book on that, remember?
I make an announcement. Both Photonics Labs and also the W in 2015 are planning to come with extensive driver assistance cars, and where they will be able to get, when you jerk from left to right or do sudden changes, and the engine will take over. That means they will slow down or take action in spite of the driver.
In spite of the driver.
In spite of the driver, and these are announced already by the VW last September.
I mean, in spite of the driver business has slight risk, especially in this country. If something bad happens, then you can't keep on saying in spite of the driver, because the ultimate responsibility on the road rests with the driver, according to just about all the laws.
They don't want to deal with the U.S.
They don't want to deal with the U.S.
I was curious, what if that red car on the screen, the driver is a hacker and he's sending the wrong signal to everyone? Is there going to be a common sense, like some kind of computer vision that would say that's a wrong signal, or?
There is work going on in trying to figure out is all the data coming okay. I mean, this is the same as any network type of thing, except it's more complicated because they're all moving around. So somehow you have to make sure that all the data makes sense, that nobody's lying, which they could do, right? But that's true with all networked information, where you're collecting information and trying to decide on some course of action. So it's a big problem. It exists. People are looking at it.